Good morning. My name is Pedro Garcés. I am a member of Civil Engineering Department of Alicante University. Well, first of all, I would like to express a word of thanks to the organizers, in particular Antonio Aguado, Esperanza Menendez, for their kind invitation. Thank you very much. My talk is about characteristic and durability of conductive cement-based multifunctional materials. It is widely known that the main function of concrete is a structural function. On the other hand, concrete is a dielectric, it's a bad conductor of electricity. However, the addition of a conductive carbon materials such as graphite powders, carbon fibers, carbon nanofibers, carbon nanotubes transforms the resulting mixture into a conductive materials. And this yields the possibility of using this material for other functions different than structural ones, so that it can be considered a multifunctional concrete. Possible functions are electrochemical ones, electrochemical chloride extraction, cathodic protection, the possibility of using a conductive cement-based material as an anode in the application of this electrochemical technique is really very interesting from the point of view of durability. Other functions not so related with durability and in which our research group are progressing in an ongoing research is the sensing function, the ability of a structural material for detecting its own deformation when subjected to some external static or vibrating load. So we are in presence of smart structures, and possible applications are structural vibration control, traffic monitoring, building safety, and structural health monitoring. And the last one is the heating and the icing function, so to control ice layer in transportation infrastructures. At present, we are participating in a European project, Intelligent Bulk Materials for Smart Transport Industries, Master Project. This is the list of the partners, being the leader Arsenal Construction. As a specific task, our contribution to Master Project is focused on the development of this sensing and the icing function. Well, we can observe here two pictures of cement-based material with the addition of carbon fibers on the left side and nanofibers. And let me introduce two concepts related with my talk. The first one is percolation threshold. In order to limit the carbonation additions, it is important to know the value of the property called percolation threshold. Percolation threshold comes when there are enough density of carbon fibers to establish a continuous path of electricity. Once the percolation threshold is not necessary to add any more carbon fibers, it makes no sense because resistivity doesn't change significantly. As the aspect ratio increased, percolation threshold was achieved at lower carbon fibers contents. In this case, this is carbon fibers of 3 millimeters length, is the yellow line. Percolation threshold is about 0.50%. For carbon fiber of 6 millimeter length is about 0.25%, and with 12 millimeters carbon fiber length is about 0.50%. Other concept related with my talk is about resistance measurement. The measurement arrangement is with sponge. We are speaking about electrolytic resistance measurement. That is sponge, a wet sponge, a copper plate, and the measurement arrangement is without the sponge, in this case using a silver pine. We are speaking about electronic resistance measurement. In a research work developed in collaboration with Carmen Andrade, here presented, the name was Electronic and electrolytic conduction of cement paste with addition of carbonaceous materials, the main conclusion, in my opinion, is the first one: the electrolytic resistance of cement-based material depends on A, the volumetric fraction and solid cement phase acting as an insulator, and porosity acting as an ionic conductor is water expression, of course. The second one is electronic conductive material added, such as carbon fibers. In the mix, the electrical resistance decreases in proportion depending on, first, the type of the carbonaceous materials, second, the size and the shape of the material, and finally, the amount added, so the volumetric fraction in the mix. And finally, the interference contact between the material and the electrode is very relevant. If conductive material are added because the traditional use of a sponge between the electrode and the specimen surface doesn't allow accounting the completed electronic conduction. Well, having said that, the objective of this research line has been always to develop electrically conductive cement matrix composites, base, mortar, and concrete, so they can be applicable to the before-mentioned function, while keeping an appropriate structural behavior and durability. Therefore, in the development of this research, we have always considered two steps. The first one, the characterization physical mechanical properties to mortar and concrete with the addition of each and every carbon materials. And the second one has been always focused in the corrosion level of the reinforcement in the formed cement-based materials. Here we can see the aspect of different carbon material use, carbon graphite powder, general purpose of carbon fibers, high performance carbon fibers, the difference are in the origin, carbon nanofibers, carbon nanotubes. Well, in the first research study, we consider the effect of different carbonaceous materials, graphite powder and carbon fibers general purpose, with different amounts, the length of the carbon fibers, and the effect of the addition of the silica fume beside the carbon fibers. We have always comparison the result obtained with the ones of the control, so without carbon fibers. We study mechanical strength, compressive, flexural, corrosion, and porosimetry. In this figure is presented the pore size distribution diameters range obtained by mercury intrusion porosimetry technique in concrete specimen with the addition of graphite powder on the left side and carbon fiber on the right. It is clear that the volume of increased mercury grows when the amount of carbon addition increases. Carbon fiber. Sorry. In this table is shown the total porosity. When the percent of carbon material is increased, it can be observed an increase in the total porosity. It is more evident for graphite powder than that for carbon fibers. In this figure, it is presented compressive strain values at 90 days of curing times of concrete specimen with addition of graphite powder. It is clear that the strain decreases when the percent of addition is increased. And the results are supported by the porosimetry. The higher porosity, so the higher level of addition, offers the lower strength. In this figure, it is presented the flexural strength values at 90 days of the specimen, of concrete specimen with addition of different amounts of carbon fibers. Flexural strength is increased with addition of fiber is increased. The high porosity is compensated by the excellent tensile properties of carbon fibers. In this figure, it is presented mechanical strength, compressive and flexural, with 0.5% of high performance carbon fiber at 28 days of curing times. regarding compressive values, only 3 millimeters fibers show good behavior. Lateral confinement is due to the lateral confinement restraint effect. By the way, when I say powder, I'm referring to carbon fibers with very short length. So, I mean, a carbon fiber powder keeps the aspect of the fibers. And regarding flexural values, improvement of flexural strength is observed. The best performance is with 3 millimeters. It's long enough to anchor and steady enough to remain straight. When local fibers are used, for example, 12 or 10 millimeters length, at high amount, they may form clusters during the concrete fabrication. It implies that 80% of carbon fiber mass is concentrated in a volume concrete of 10 or 20% only. And consequently, drop the mechanical strength of the samples, and mainly the bending strength and slightly the compressive strength. And therefore, chemical and physical treatments are necessary to achieve an homogeneous distribution. In this figure, it shows compressive strength with 0.5 of carbon fibers and silica fume at 28 days, occurring times of concrete specimen with addition of both materials. Silica fume is added to the mixture in order to increase the strength. It's a regular practice of almost all official standards. The presence of silica fume contributes to improve the distribution of the carbon fibers and also improve the functionalization of this product. However, due to the small particle size, several techniques have been developed to reduce the overall volume. And suppliers offer this product with different particle distribution. And often, users are not aware of it. Here we can observe the particle size, densified, semi-densified, and the same silica fume after being treated with a physical process, sonication process. And the difference of the particle size are very relevant. And coherent with that are the results of compressive strength. This is concrete with carbon fibers, but without silica fume. This is with densified silica fume, semi-densified silica fume, and after being treated with sonication process. And the difference are really of the strengths are really very significant. On the other hand, different oxidation treatments were applied to the different carbon materials to assess the influence of the modification of the carbon material sulfides in the interaction between cement paste and the carbon materials. And oxidation by air at 400 Celsius degrees yields the highest amount of oxygen sulfide groups, thus producing better interaction with cement paste. And coherent with the result, it has the resistance characteristics. Oxidation in air at 410 degrees Celsius is the most efficient to improve the mechanical properties of cement mortars incorporating these carbon materials. Also enhance physical anchorage of the carbon material to cement paste and due to increase in the roughness of the carbon fiber surface. Other carbon materials are carbon nanofibers. Carbon nanofibers are one of the additions that can be used to create multifunctional materials. More or less, an increase of about 5% of compressive strength can be achieved for every 1% of carbon nanofiber added to the mortars. As not major modification in density, C scale, the hypothesis of carbon nanofibers as reinforcement for the Feynman matrix could be consistent. And the increase of carbon nanofiber dosage doesn't significantly affect the flexural strength. This is a very different behavior as compared with carbon fibers. And similar behavior was observed with carbon nanotubes. In this figure, bending strength and compressive strength mortars with different dosage of carbon nanotubes at 7 and 28 days was observed. And it is clear that the increase in carbon nanotube dosage doesn't significantly affect bending and compressive strength at this period of curing time. On the other hand, new bioenergy manufacture involves neither the emission of pollutant gases nor high energy consumption is a much research used today. Perhaps the more important example is alkaline cement. In this figure, we can observe an electron microscopic image of alkali activated slag mortars with 3% of carbon fibers. Water glass, slag cements, and concrete are characterized by their ability to develop a strength comparable to the strength of Portland cement. Higher addition of carbon fibers led to higher bending strength, as expected. However, the most important effect of carbon fibers in these particular binders are related to the drying screen shrinkage. And this value was around 3 times to 4 times lower in Portland cement, which is the solid points, or line almost superimposed, than in alkali activated slag mortars. In Portland cement, mortar's ring sketch is inaltered by the fibers, and in alkali activated slag mortars, the inclusion of carbon fibers, this is without carbon fibers, this is 1% of carbon fibers, this is 3% of carbon fibers, has a clearly beneficial effect. The shrinkage declines by up to 50% with the rising in proportion of fibers. And that is really important in these particular binders. Well, I have established that the second stage was always focused on the corrosion level of reinforcements in the formed cement-based materials. Here it is presented corrosion rate of reinforcements and concrete specimen with addition of carbon fibers in introducing a solution of sodium chloride. Corrosion rate decreases when the percent of graphite powder increases. It was an unexpected result. First, graphite powder is a conductive material, so concrete resistivity decreases. And it implies that, and on the other hand, we should take into account the effect of galvanic couple. Carbon is more noble than iron, so it implies the development of the corrosion cell and an increase in corrosion rate. However, corrosion rate should increase with the percent of graphite powder added to the mix. Different hypotheses could be considered. The first one, a contact between carbon particle and steel is established. So there is a contribution to kinetic corrosion kinetic, steel and carbon materials. So corrosion intensity decreases. The second one, the most important in my opinion, is the oxygen absorption in the carbon particle hinders heat diffusion. Most of the corrosion process in the development of this processes, a cathodic control is produced, and in this case, this is important. When the percent of graphite powder is higher, the corrosion intensity is lower. And finally, we have observed that the contact between steel and carbon implies a shift to more positive values of potential corrosion, so more compact passive layer in the steel surface, and so the lower corrosion intensity. Nevertheless, when we consider other cement matrices and other carbon addition, such as carbon nanofibers, the corrosion intensity increases slightly when the amount of carbon nanofibers in cement paste increase. This was expected. And similar behavior was observed with carbon nanotubes paste. Corrosion intensity increases slightly with the amount of carbon nanotubes in cement paste increase. It's not very significantly, but it's clear. So the main conclusion could be that the addition of carbon materials to the concrete can improve its mechanical properties and produces different levels of corrosion depending on the type of carbon material or cement-based materials. I have mentioned that the electrochemical application function is very interesting from the point of view of durability. This is techniques, electrochemical chloride extraction, cathodic protection, consists in applying a current density between the steel reinforcement connected to the negative pole, cathode, and an externally deposited electrode acting as an anode connecting to the positive pole. This is a traditional stainless steel or titanium-ruthenium side wire mesh. This is our proposal, a conductive cement paste. Since chloride are negatively charged ions, the imposed force fields cause them to migrate from the rebar to the outside, without the need or the movement the concrete affected by a high concentration of chlorides. Regarding the experimental process, first we prepare the concrete specimens, then after 28 days of curing time is the node placement in our proposal by uniting the conductive cement paste over the surface, or applied like a plaster. Then the electrolytic replacement. A wetting system based on drip filtration is attached around the sponge in order to ensure the liquid is in contact with the node. And the other possibility, only in our proposal, is watering the surface periodically, only feasible using a conductive cement paste due to the high level of porosity, allowing maintenance an adequate level of moisture. Then the electrochemical parameters, the current density and the applied charge. Then different samples was obtained at different depths. Then a chemical analysis of chlorides. And then obtaining the distribution profile and mass balance. This is the result obtained with a traditional anode. Yellow line at the initial distribution profile of chlorides. The purple is the final distribution profile chlorides, and the green is the efficiency. In any case, almost 80% of chlorides were extracted, and similar behavior with our proposal, with our conductive cement paste, more or less 80%. Well, the potential advantage when compared to other traditional nodes, our proposal is the possibility of application as a final layer by uniting. The efficiency are very similar. The adaptation to various types of surface, vertical to more compressive, very important. The possibility of reutilization, and to summarize, the versatility of the paste. Our ongoing research is a combined treatment of electrochemical chloride extraction and then cathodic protection. This treatment is able to provide protection conditions to steel despite several internal and external chloride contamination, as long as the proper current density value is set. According to the chloride content present, the 100 millivolt decay criterion was fulfilled. Thank you very much.